Hi folks, this is activity number 4 for lab number 3. So I have a geometry like that which I refer to it as a C-clamp and made of aluminum with these material properties. Now I'm not going to be changing material properties here, but I will use the default properties in Catia. Okay, we know that the inside of this hole is all clamped, it's fixed, and this face that you see here is somehow, which may not be realistic, but this face is pushed down by 100th of an inch. Okay? Now, first of all, you're supposed to use, in general, you're supposed to use as many planes as symmetry. And if you look at this problem, the way I described it for you, all you need to do is half of this thickness. Okay, so you can split this thing into two pieces, but in this analysis, in this problem today, uh, initially I am not going to cut it. I'm going to, uh, I'm going to make the whole model. Okay, but later on I'm going to cut it. Okay, so let's go make it. Some dimensions are given here. These are all inches, so let's go there. So we start with a new part. Immediately, I'm going to save it in the folder that I prepared. File, save management, save as. Let me move up. Activity number 4. I'll call it problem 4. Problem 4. Okay, good. Now let's make it. On that plane, on that vertical plane, I will sketch something like that C. We'll dimension in just a second. Maybe like this, like so, like so. Do it any way you want. You have to get something like this geometry. Now we're going to dimension this thing. So first of all, let me make it symmetric with respect to top and the bottom. That's very easy. If I put the center on that line, it's going to become symmetric. Yeah, because of the way I've done it. This control that under constraints defined in a dialog box. We make it coincident. Believe me, this is going to be symmetric because of the way these circles are drawn and these are tangent to it, etc. Now let's put some dimensions. So double click here. I think this guy is 3 inches. 3 inches. Okay, good. And that guy is 1 inch. Automatic. What did I do here? Let's try it again. 3 inches. Okay. This guy is 1 inch. Automatically it adjusts the radius of the circle so that it fits this constraint. Good. Now we also have a circle up here. Okay, and the circle I'm going to put it there and dimension it now. So the radius of the circle is, what is the radius of the circle? Is 0.25, the diameter 0.5, and it's symmetrically positioned. So from here, I'll do it like this on purpose. I can say from here to here is 1. I can do that, but I'm going to do it a different way. This guy control that guy control the center. You make it constrained. You define a dialog box equidistant. You could have done from here to here half an inch. Now I have no choice but to do it from there to there a half an inch, 0.5. Okay, exit, pad it, but I'm going to do it symmetrically because later on I want to cut it. It's easier for me to do it this way. That width is, I believe, if I'm not mistaken, that width is 2 inches. So yeah, so make 1 inch in each direction. That doesn't look right. Half an inch in each direction, sorry. 0.5, half an inch in each direction. Good. And we save everything. Now we apply material properties on it. Aluminum, default properties, aluminum. If you want to change those, you just double click on this thing, go and change the appropriate boxes in the dialog box that opens up. Now, we're going to go to start, analysis and simulation, generative structure analysis. Catia immediately meshes it, although I caution you that you want to have a finer mesh in this area. Let me do that for you. Let me remind you how I did in activity number 3 of lab 3. So you go open this up, local mesh size on that face. Well, already it made it smaller, but I'm going to make it 0.1. How about that? Very small, tiny. There. Now, if you look at your mesh, right-click mesh visualization, you see that there's a finer mesh in this area than the rest of this thing. And you can do similar thing in other places. So let's deactivate that. All right. So what I'm going to do, we're told that inside of this thing is whole, clamp is inside of this thing is clamped. Select that. Everything is clamped there. And you're told that this face is pushed down by some amount. First of all, you don't know by how much. So uh, you don't know how much force is needed to do that. And this value downward is 0.01, okay? So in Catia, if you want to apply a non-zero displacement, first you have to make it zero. So I'm going to click on this user define. I say on that face, in the direction Z, 0. That means 0 on that face in the direction Z. That's what this thing said. Now that you did this, you can go and say, here's an icon says enforce displacement. You click on it and you select that. You select that constraints that you put in there or restraint that you put in there. Let me show you. You just made this. You just made this right there. See that? If you select that, it slides up. And it says, okay, I don't want it to be 0. I want it to be negative 0.01. In Catia, you have to do this thing in 2 steps. First, you make it 0, and then you can change it. Say OK. All right. And pretty much it. Let's save the analysis. File, save management, analysis, save as. That goes into the correct folder, which is activity 4. I'll call this thing problem 4. Let me say OK. Now we can run it. Here is the icon, Catia compute icon. You click on it. Hopefully nothing went wrong. We don't have rigid body motion, all the strain. So you click on this icon, deformation. It shows you an animated. That's the way it should be, right? It should be like that. Now, if you want to look at the displacement, that last icon gives you displacement. And if you wonder, well, wait a minute, didn't I push this thing down by 0.01? Why did it go 0.0116 more? That's because this is actually the vector of these displacements. Notice that if you put the cursor on it, on any of these arrows, you see that? If you put the cursor on any one of these, the last component is negative 0.01. But these other ones, because it goes to the left, it goes this way, and therefore that's why the vector is going to be a little bit bigger. Square root of these things squared is going to give you that number that's bigger than 1. Now, if you want to see uh, the nice contour, so just double click on this or double click on that line under visualization, average ISO, and there we are. Okay. Now, the question is, how much force is needed to do this? First of all, let me deactivate that. How much force is needed to push this thing down? So you go to sensor, this is very important, right click, uh, create a resultant sensor, see that? You put it on sensor, right click, Go down, create a resultant sensor, and you say reaction sensor. You click on it, and it's on this stuff, on this restraint, that you want to show how much force is resisting it. Or you can put it on the clamp also. See that? Because the force resisting it on the clamp is the same thing that's needed to push this thing down. But that's entirely up to you. You select on it and you say update. See that? Update, and you're going to get 93 pounds. Downward 93 pounds. The reason I showed you this is that the next in in on the test, one of the questions that I'm going to ask you in a particular problem is how much force is needed to create this displacement. So in that box, you have to put the right number. But just remember, this is 93, but I want to cut this thing and see what the effect is going to be. All right. So first thing, I'm too lazy. I don't want to go and redo this thing. So all I do is I go to uh, my part, expand the tree link manager, expand, you go back to the part right there, okay? And I'm going to cut it, split it, split right there, split the saw. You click it, you select that plane. Doesn't matter which side you pick, you're going to get this. Go back to the analysis, go back to the analysis. You can you can double click on any one of these, will take you back to analysis, doesn't matter. Now don't forget to put surface slider on the back face. On the back face, okay, and run it. Because we cut it, we have to run it again. Notice that the thing that may have bothered you here just disappeared. The clamp is still there. It was extending out there because of the fact that we split it and didn't know. Ignore that and then run it. Okay? So, if you look at the deformation, same thing. If you look at the stress, very small. Biggest stress are in this area. Okay, we know that. And if you look at displacement, it's going to be also the same thing as before. No difference. However, when you go to the sensor, and you already created that sensor, see that? You already created that. It's not going to go away. Double click on it and say, select it. Once again, you select it and you say update. See, half of 96 that we got before, or 90, whatever, 93 that we got before, half of it. So if you see a question, how much force is needed to create the following, the deformation described? This is not the problem that you're interested in. The problem you're interested in is entire thickness. But because I asked you to use as many planes of symmetry, you use the plane of symmetry. And this is the value that you get for the sensor for half of this. The other half is still there. So in that box, as your answer, you cannot write this. You have to write double of that. Okay? Just so that there is no misunderstanding uh, with this issue. If I gave you this problem and I said use as many planes of symmetry, obviously you're going to cut it like this. And then it says once you run it, what is the force needed to create this deformation? Because you're getting the sensor on half of it, you have to take this and multiply it by 2 and write it in that box. Please, I don't want any misunderstanding. Okay, so that takes care of this last activity. Good luck.